Right, welcome back. So our next topic that we're going to chat about is continuity, differentiability, and limits to infinity. These are all grade 11 topics, and they actually are very nice and easy questions to score well on. Okay, so let's have a look at continuity. As you understand continuity in nature, like the continuous flow of water, so we have exactly the same thing in maths. If I have a function, and if my graph is continuous, it means that if I take my pen and I draw along this curve, I do not lift my pen up at any point. Okay, and that makes a graph continuous. All right, but unfortunately that definition doesn't suffice, so we have to use a nice looking mathematical definition. So if you look here, the mathematical definition is the limit as x tends to a from the left of f of x. And remember, the limit is basically your y value as x approaches that point is equal to the limit as x tends to a from the right of f of x is in fact equal to f of a. So if I look at a particular point on the graph here, I can see that as I approach the graph, as I approach this x value from the left-hand side, I'm going to get the same y value as if I approached the graph, that particular x value from the right-hand side. Okay. Now, the minute that this formula is not in balance, okay, it's when we have our discontinuities. And I'm sure you're familiar with them, but basically what do we have? We have our removable discontinuity, and just as the statement says, you can see that there is a hole in the graph, okay, and so I can see it's not continuous because as I put my pen and I go towards or go along the graph, I can see I'm going to have a hole in the graph, so I have to lift my pen and start again. All right, and so therefore it is a removable discontinuity. So if I look at it, the limit from the left gives me that y value, and the limit from the right towards that point will also give me the same y value, but f of x at that particular point will give me a different value, and so therefore my formula is out of balance. Okay, so so basically that's the definition of a removable discontinuity, and the other discontinuity that we have is a jump discontinuity. All right, and just as the graph depicts, you can see that you're going to have the limit from the left goes to a particular point, then we jump, and the limit from the right goes to another point. There's a clear jump in the graph. Okay, and so basically my formula is out of balance because the limit from the left is not equal to the limit from the right. All right, now the key with these questions is to get your notation correct. Okay, so if I'm looking at the kind of breaks in the graph, I'm looking at -4, -2, and 1, I can see that at -4, this graph is continuous, as I can, there goes my pen right through that point. Okay, but when I'm actually, I can't just say when at x equals to -4, the graph is continuous. I have to set it out correctly. And many people actually lose marks on this section because of just not laying it out correctly. So let's have a look. We would say at x equals -4, we would say the function is continuous because the limit as x tends to -4 from the left of the function f of x is equal to the limit as x tends to -4 from the right of f of x, which in fact is equal to f of -4 is equal to 3. You must make sure you write that whole statement if you want to get your 4 or 5 marks. Okay, what happens at x equals -2? We're going to say we can see there's a nice hole in the graph, so there's a removable discontinuity, which means that how are we going to write this? We're going to say the limit from the left is equal to the limit from the right of f of x. They're both equal to 4, but the problem is f of -2 does not exist. Okay, and the same with at x equals 1. We're going to say there's a jump discontinuity, and that means that the limit from the left is different to the limit from the right. Okay, all right, so remember notation, notation, notation. All right, so let's have a look at the 3 different ways that this question could be asked. Okay, so you could be asked to, first of all, sketch the graph and then discuss and classify any discontinuities that you can see. Okay, and generally we bring this topic into piecewise or split functions because we want to know what happens when we when we transition from one function into the next, is it a smooth transition, or is there a jump discontinuity, or is there maybe a hole in the graph? And so that's why this question gets asked in this particular topic. Okay, so if I'm asked to sketch this graph, it's because they haven't given me a domain of less than 0 or minus 180 to 0 or minus pi to 0 rather, you only need to sketch the graph just before it. Okay, so if you kind of go and say, hold on, I know there's a turning point there, but minus pi over 2, I can see it's a cos graph, and I know that the upper boundary or the end point is when x is 0, so cos of 0 is 1, and 1 times 4 is 4. Why is there an open circle? Because it is not including. I then go into my parabola, make sure that when you calculate this, obviously you've got to show turning points, but you also work out your endpoints. So work out what happens when x is 0 and what happens when x is 3. Both of these would have an open circle at either endpoint. Okay. Now the problem with this is because it's not an open circle, it means because in the next function they have the same value. So when I substitute 3 into my straight line, 3 2s are 6 minus 5 is 1, I'm going to get the same value as that endpoint. So that hole then gets secured. Okay, all right, so from drawing this graph, and just remember to label all intercepts and all turning points. All right, now I go to the next question, and it says discuss and classify any discontinuities. Okay, it doesn't say just at the difference, so I don't need to talk about x equals 3 at this stage, just the discontinuity. So I'm looking at x equals 0. And I can see there's a hole in my graph there. So what do? I write it out beautifully. Okay, and I say at x equals 0, the limit from the left as x tends to 0 of the function 4 cos x, and I put 0 into x's place, and I end up equaling 4. Okay, I then do the same thing from the right-hand side, and I say the limit as x tends to 0 now from the right-hand side, so I'm looking at the parabola. I substitute 0 into the parabola, and I get 4. But I can see that f of 0 does not exist, okay, because it's open, or not included, and so therefore there is a removable discontinuity at x equals 0. Please just be very careful when you set out these questions. Many marks get lost. Okay, the next question is f differentiable at x equals 3? Okay, now there are two parts to a function being differentiable. Obviously, by the nature of the word differentiable, basically they're saying that is the gradient from the left equal to the gradient from the right. Okay, but before we can do that, there is kind of a prerequisite, and that is that the graph has to be continuous through that point x equals 3. So I can see it is. Okay, but I have to show it. So I'm going to say at x equals 3, the limit as x tends to 3 from the left of f of x is equal to 1. The limit as x tends to 3 from the right is also equal to 1, and f of 3 is equal to 1. And so therefore my nice little formula that I put in, and so my function is continuous at x equals 3. Okay, then I'm looking and saying, okay, hold on. Now I can say, part 1 done. Now I want to know, is it differentiable? In other words, is the derivative, so now the limit of the derivative from the left, is it the same as the limit of the derivative from the right? Okay, so now I'm going to say the limit as x tends to 3 from the left of the derivative. So I'm looking at this function here. It's a nice little chain rule. Hop it down to differentiate, and the derivative of the bracket is 1, and I substitute 3 into x's place, and I'll get 2. Okay, I then take the limit as x tends to 3 from the right, so I'm now looking at the straight line. Remember, the derivative of a straight line is always constant, so it's 2, and so therefore, because my limit of the derivative is from the left is equal to the limit of the derivative from the right, I can say, therefore, my function is differentiable. You do not need to write this. This is just for you to be reminded of the definition. Okay. All right. I hope that makes sense. It's easy marks. All right. The backwards way is when you get told that a function is continuous or differentiable and you have to solve for any unknown variables. Okay. All right. So if you look at part 1, it says find A if f is continuous at x equals 1. So now remember, if it is continuous, we're basically saying the limit from the left is equal to the limit from the right is equal to f of 1. Okay. So we start with this. Now, even if you can see what your simultaneous or what your equation is going to look like, please, guys, it's very important that you put the notation. Otherwise, you end up with half your marks. Okay, so let's have a look at the limit as x tends to 1 from the left, minus 4 ln x plus 5. I put 1 into x's place. Remember, the ln of 1 is 0, so I end up with it being 5. I then take the limit from the right, and I put then into my parabola, and I put 1 into x's place, and I get 3 plus a. Okay, and obviously f of 1 is exactly the same. Because it's continuous, I can make them equal to each other, and I get a equal to. Please do not jump to this step. Okay, it's happened a few times in past in past exam papers, and you end up with half your marks. Okay, the notation is key. All right, so then the next question here is f differentiable at x equals 1? Now, remember, we don't need to now prove that it is continuous at x equals 1 because it's already told us that it's continuous at 1. So our first statement is saying that f is in fact continuous at x equals 1, and I can now plunge straight into finding the derivative of both functions. So I'm going to start with saying the limit as x tends to 1 from the left. So I'm looking at my ln function of the derivative. Okay. Now remember, it's going to be minus 4 times the derivative of ln x. And the derivative of ln x is 1 over x plus the derivative of a constant is 0. Okay. So I have minus 4 over x. I put 1 into x's place, and I get my answer to be negative 4. Right, now I need to double check if the limit from the right is the same. So I'm going to go to my parabola, and the derivative of a constant is 0. Hop this down, I get 2ax. We already know a is 2, so I get 4x. Substitute 1 into x's place, and I get 4. These are clearly not the same. So therefore, because the limit as x tends to 1 from the left of the derivative is not the same as the limit as x tends to 1 from the right of the derivative, we can say that it is not differentiable at x equals 1. Okay, as I say, I can't stress enough notation, notation, notation. All right, then this is an awesome question, and it is more of an applied question to these topics. Okay, so let's have a look here. I've got a nice function graph here, a split function graph, and I've got an absolute value, and then I've got an exponential graph. Okay, so the first part of the question is explain why h of x is not differentiable at x equals 1. Remember, differentiable, there's got to be 2 components. Continuous first, then we look at the gradients. Okay, so let's look at what happens at x equals 1. So I can see at x equals 1, there is a hole in the graph. That means it is not continuous. So I do not go further, and that is why it is not differentiable at x equals 1. Okay. Why is it not differentiable at x equals minus 4? Let's look at what happens at x equals minus 4. I can see that at x equals minus 4, it's certainly continuous because my graph goes right through that point, but the gradient from the left is positive, and the gradient from the right is negative. So therefore, it is definitely not differentiable as the gradients are not the same. Okay, then a nice easy question, basically finding the equation of the absolute value. Okay, so you've got your a, x minus b plus c, and you have to determine the values of a, b, and c. Okay, so if I look at a, I can see from the shape of my graph is negative because it's an unhappy absolute value, and I know that if this gradient will be the positive version and that will be the negative version. So I'm going to look at one of these 2 straight line graphs. And because I know this point and I know that point, I'm just going to use the nice grade 9 method of rise and run. Okay, so to get to that point, I'm going to drop 4 units and I'm going to run 4 units. So my gradient is basically negative 1. And remember, A is negative 1 because of the shape of the graph. How do I get my B and C? Well, if I know the coordinates of my snap point, which I do because I can read them off, Okay, I know that inside the absolute value must be plus 4, which means that B must equal to negative 4 and C must be plus 4. Okay, hope that's nice and easy. All right, then let's look at some application questions. So if I look at this question, it says, so now I've got my equation written up here, and the next question is determine M if H of M is equal to 10. Okay, so now they're giving me the Y value is 10 and the X value is M. So I'm looking at my absolute value and it doesn't go as high as 10 on my Y. So I have to substitute into the exponential graph to see what happens when X is 10, what is my M value. Okay, and so it's a straightforward substitution. I put 10 into Y's place and I put M into X's place and I solve, and it's a nice lin. I look at my answer, 1.95. It makes sense. Always check. Okay. And so that's, yeah, nice and easy. All right, then I look at this question here, and it says the inverse function of 4. So now I don't want to redraw this. This is my h of x. I don't want to draw this now. I don't want to draw the inverse of the graph, okay? But what do I know about the relationship between the inverse function and a normal function? And that is that x and y is swapped. Okay, everything, x and y swapped. If it's an x-intercept, it changes to a y-intercept. If it's a vertical asymptote, it changes to a horizontal asymptote. So if I look at this, this is basically, if I want to know the inverse function of x, it's equivalent to the y value of the original. Okay, so what I basically want to know is if the y value of the original is 4, what are the corresponding x values? So just looking at the graph, I can see that I'm going to have 2 possible values, and that is at negative 8 or at 0. Okay, and so that will give me my y values for my original, or my x values for my original, or my y values for the inverse. Okay, just go through that slowly. All right, and then this next last question, I see I jumped the gun here with that answer, so let's just go back. All right, let's have a look at this. If I'm asking for h of the derivative of negative 5, it really is just an application, do you understand, and it's a composite function. Okay, so remember we always start with the inside bracket. So if I'm asking for the derivative when x is negative 5, I'm basically asking what is the gradient when x is negative 5. So I go to next x is negative 5, and remember the gradient of this is going to be 1. So I want to know what is h of 1, because I'm going to replace the derivative when x is negative 5 with 1, and then I go to h of 1, and I look and I see a problem, hole in the graph, undefined. Okay. All right, now what I want you to do is remember you've just got to practice this section. All right, and so make sure you go through that revision. Okay, the last thing we need to do in this particular topic is our limits to infinity. Now, this is another grade 11 topic, and I think it's one that you know very well. Generally, we use it to find the horizontal asymptote, but if you get asked to find it in like a question on its own, remember that how do we find the limits to infinity? We basically change every term to either be a fraction, or to have the x in the denominator, or to have a constant. And the reason is, if you think about it as a graph, this would be a hyperbola, and as x gets bigger and bigger, so my graph gets closer and closer to 0. But also just logically, the bigger my denominator is, the closer my fraction is to 0. So if I've got 1 over 10 versus 1 over 1,000, I'm getting closer and closer and closer to 0. Okay, so you basically change every term into that. So how do we do that? If I take the limit as x tends to infinity, I look at the degree, okay, and I divide the top and the bottom by the highest degree in the expression. Okay, and I look and I've got x squared and x squared, so I'm going to divide through every term by x squared, because what am I really doing? I'm dividing the top by x squared and the bottom by x squared, which means I'm dividing by 1. So I'm not changing the value. You do not need to show this step. You can actually go straight into this, and you can in fact even go straight into the answer. Okay. All right, so that's a nice easy one. And if I did ask you for the horizontal asymptote, which we'll do later when we do rational functions, you would say there's a horizontal asymptote at y equals 3. All right, but let's look at some trickier ones. So if you have got the limit to infinity and you've got a surd, okay, then you're going to say, all right, hold on, I do know that the square root of x squared is x. So what I'm really doing, if I divide the numerator, every term inside the numerator by x, the square root of x squared or x squared, I'm really dividing by x. So if it's inside the square root of x squared, or inside the square root rather, I divide each term by x squared, and if it's outside the square root, I divide each term by x. I'm really dividing by x over x. Okay, hopefully that makes sense. So go through it, each term by x squared. Okay, I've really done every step so that you can see it, but you do not need to fill in every step when you write this in the exam. And so I get the limit as x tends to infinity. Obviously, that's going to end up being 0. That's going to end up being 0. So I want the limit as x tends to infinity. So what's the square root of 4 over 2? And it's going to be 1. Okay, now watch out for this sneaky bugger here. So if I've got the limit as x tends to infinity of this bracket here. Now, the problem is there is no denominator. Okay, that means you can't just sum and divide because then you are changing the value. So what do we have to do? We have to create a denominator without changing this value so that we can just divide the top and the bottom by x squared or root x or whatever it is. Okay, so what am I going to do? I'm going to multiply by the conjugate, the numerator and the denominator by the conjugate of this expression. Okay, so if you look here, you've got the surd minus root x times by the surd plus x. Okay, which means that I can then apply dots and I simplify it like that, and obviously my x squareds are going to cancel, and I end up with 2x over root x squared plus 2x plus x. Now I've got it exactly how I like it. I can divide the top by x and the bottom or inside the square root by x squared and outside the square root by x. Okay, so have a look at that. 2x over x, inside the square root over x squared, outside the square root by x. Okay, and so I'm left with 2 over 1 plus 1, and I've got 1. Okay, so watch out for those sneaky dudes, all right? But otherwise, this is a nice, easy section. That doesn't mean that you mustn't practice them. Okay, good luck.